So in 2 dimensions, we might be interested in making a statement about what is dq. And so dq will be equal to the volumetric flow rate that's passing through here, plus the volumetric flow rate that's passing through here. And so we would write this as v dot n dA. And this is for an arbitrary orientation. And so this would be equal to Vx times dy plus, and then this would be minus Vy times dx. So, so here would be our positive velocity in this direction and a negative velocity in that direction. And v dot n dA is the 2D equivalent of this statement that we've made right here. So if I combine that with my definition of the stream line, I can write that Vx is given by nothing but d psi by dy multiplied by dy. And then we've got a minus Vy here, and minus Vy is going to be written in terms of the d psi dx, and so the minus signs will cancel, so this will be plus minus minus d psi by dx. So my conclusion at the end of the day is that dq is exactly the same as d psi. In other words, the size or the step d psi tells me about the volumetric flow rate passing between 2 neighboring streamlines. And a very good exercise to do is to make sure that you try substituting, if this is a general statement for n, and you take a general statement for v and dA, that when you do this, that if you take this and you combine this with this, that you'll indeed see that when I take Vx, I'll dot it into with dy, give me this. The area is nothing but this quantity right here, so it will cancel. And similarly, then when I take v dot n and I take the y component of it, then I'll get this component of n and the vy component that I'll get right here, and the minus sign here, and we end up with this term. So, so you can check directly by substituting this in here, but what I've done is right. So this is a particularly useful result, that if we see 2 contours or streamlines with particular values of psi, then we can say something about how much flow is going between them. The one final thing that we might do is we might think about what happens if I took, and as I said, A and B are arbitrary points. So these are arbitrary points. So what about if I hypothetically took 2 points, let's say this was point A and this was point B. What about if I took 2 points along the same streamline? So we might say, what about along the same streamline? Well, we know that the definition of a streamline, which we wrote down at the very beginning, was that along the same streamline, dx by Vx was equal to dy by Vy. In other words, along the streamline, the velocity is indeed tangent to the streamline. This would be dys, and this would be dxs, and the velocity would be parallel to this. So if I just rearrange this and I compare it with the expression that I have above right here, you can see that that if I can rewrite this expression as Vx times dys minus Vy times dxs, which is this term and this term. And if they were equal to each other, then when I write it this way, then this will be equal to dq, which is equal to 0. And so sure enough, as we said in class, there is no flow rate across a streamline. And again, a streamline would correspond to d psi is equal to 0, or equivalently, psi is equal to a constant. So in fluid mechanics, it's very common to show a flow where people will indeed draw a flow, and they will just draw different values of the streamlines. We will understand that, that everywhere locally to here, we can see the velocity. And in particular, the distance between two streamlines is telling me something about all the flow that's going between that. So if the streamlines move further apart, then the velocity is slower. Now we can tie that into something that we've done in class today, where we talked about conservation of mass. And its connection to the streamline. And in particular, we saw that conservation of mass corresponded to del dot V was equal to 0 for the particular case of an incompressible flow. So in other words, in words, we might say that it's divergence free. Okay. Well, if we combine that with our definition of this, then we know that we might write this as dvx by dx plus dvy, where dy is equal to 0 for an incompressible flow in 2D. So this is a 2D incompressible flow. And the final thing we might do is substitute in for our streamline, our expression for our streamline. So we could substitute in here for d by dx, and we know that vx is equal to d psi by dy, and vy was equal to minus d psi by dx. And so we end up with a statement that looks like this. Oops, y dx. And so this, indeed, by the equality of mixed partial derivatives, is indeed equal to 0. And so you can see that the stream function is a particularly useful way of drawing things, because indeed it satisfies in 2D that the divergence of the velocity field is going to be 0. And so we know that all of the mass coming through here is going to be the same as all the mass that's going through there, is going to be the same as all the mass that's going through there. So if we see areas getting wider, then we know that locally in the region where the area gets wider, we know that the velocity through here will be smaller. Where the area gets smaller, then we know that the velocity will be bigger. And so drawing stream functions is a very powerful way of seeing what's going on in a flow.